Morning. How y'all doing? It's my first time in Sweden. I got to visit Max last night. Are you familiar with Max? That's a delicacy we don't have in the United States. Uh, yeah. So I had a one star Michelin meal last night, and then went to Max's for a veggie no chicken sandwich. It was delightful. So I guess my job is to impart some knowledge. What do you call it? Hardcore technical knowledge or something. And I intend to do so. I intend to impart negative knowledge. So if I've succeeded, at the end of this talk, you will all know less than you currently do. Hopefully I'll succeed, but we'll see. So basically, you could see my talk as sort of a follow-up to many of the things Martin was talking about in terms of being open-minded and being willing to rethink things, and the fact that 5-year-olds in many ways are more creative than people who have education. And one of the dangers of having education is that you can end up thinking you know what you're doing, which is the most dangerous thing you can possibly think, right? And so Brett Victor's talked about this, for example. The most dangerous thought a creative person can have is to think they know what they're doing. And I will make a personal admission that I've been programming for almost 40 years. I used to be a professional software developer. I have a PhD in programming languages, and I do not know what a variable is. Okay, I used to. The last time I knew what a variable was probably around 2004, maybe 2003. I thought I knew what a variable was in 1980 when I first started programming in BASIC. I definitely don't know what a variable is now, and I'm going to try to convince you that maybe you don't know what a variable is also, or at least the notion of what we consider a variable should be much broader than what we normally think about. And there are a couple of points to this talk. First of all, I just want to show you some things that maybe you haven't seen before. In fact, I think that's quite likely if you haven't done a whole lot of different styles of programming. Probably you'll see something you haven't seen before, I hope. But beyond that, I want you to think a little bit about what Martin said, that most of the things that are out there still have yet to be discovered. Okay, so my view is that computer science is likely to be like math or physics in that we've been doing it for a very short period of time currently, and if you look at the history of math and physics, it took hundreds of years for people really to have any idea of what was going on. We've only been doing computation, sort of theoretical computation, arguably since the 1930s. And as far as having modern hardware, that's maybe been since the late 40s or early 50s. So it's a very young field. And I think that many of the things that we've ended up with today are effectively accidental. If you look at things like Windows and Unix, I think those are very much accidental technologies. Those aren't things that had to have been developed. If we encounter some aliens in the future, I think it's quite unlikely that they're going to be running Microsoft Windows. I don't think there's anything fundamental about Windows, or Unix for that matter. So, and if you look at the history of computing, there are all sorts of other very different operating systems that have existed over the years. And in fact, if you look at Smalltalk, that was a radically different operating system in that the idea has no operating system at all. The idea of Smalltalk is that an operating system is a bad idea. You shouldn't have an operating system. You shouldn't have applications. You should just have objects that are communicating with each other via messages. That's much more important and fundamental. And that many of the problems we currently have are basically because we've siloed different parts of our computation in these applications and operating systems that we can't change dynamically. And I think it's a similar circumstance with programming languages. I think the programming languages that are currently popular and currently in use, reflect a very small, range of all the possible programming language ideas and paradigms that currently exist. I'm just curious, how many people here program in C Sharp? Okay, and how many people program in Java? Okay, Python? Ruby? Okay, how about C++? All right, so to me, those are all exactly the same language in a way that I hope to make clear. Um, and if you're looking at it from this particular lens of what a variable is, they are exactly the same language. And there are many other different types of languages that are completely different in theory. And they work very differently, have a totally different view of what a variable is than any of those languages. And I guess the idea is that if even something that seems so basic, something we learn at the very beginning of programming, what a variable is, if that notion can actually have wildly divergent ideas behind it, if there are many different ideas of what a variable is, they're completely radically different than what you see in those mainstream languages, then what else do we still have to learn? And the other message I have, which is partly aimed at everyone in this audience, and myself included, but also partly aimed at programming language researchers and other people who want to try to understand about programming languages and programming paradigms, is that I think we've largely given up on trying to come up with new ideas in certainly the field of programming languages. That we've spent almost all of our time basically trying to make incremental improvements to things that already exist. And if you look at the history of programming languages in the 1960s, early 1970s, you see there's tremendous energy. And people back in the 1960s knew they didn't know what they were doing. There really weren't computer scientists in terms of people getting computer science degrees in the early 1960s, for example. So you had mathematicians and physicists and people coming from psychology, for example. And they brought in all these different ideas. They didn't know what they were doing, so they had to invent a bunch of things. And so you can see that these paradigms were being created that we still use today. And I think that there are many other paradigms that are left to be discovered and that we've basically given up on the idea that they're out there. We just sort of take the existing paradigms as granted. And so I want to challenge that also and instill maybe a little sense of how to say, sort of dissatisfaction, right? I think it's important to be a little dissatisfied with the way we do things. So now let's say that we should give up hope or not enjoy programming. I love programming. It's, I think, extremely interesting and intellectually stimulating, and it's great to be able to solve real problems for people and so forth. But at the same time, I think there's a danger in being a little too proud of what we're able to accomplish with current technology. And we should always want to be able to reach for the next thing, okay? And sometimes it means that we have to be willing to take a step back. This is the hard thing, okay? So in the 1960s, in some sense, they had a much easier job. Not because the paradigms had yet to be discovered. I think there's still many paradigms yet to be discovered. But because things weren't standardized to the extent they are now. We didn't have JavaScript. We didn't have Windows. We didn't have the Intel architecture being dominant or ARM becoming dominant, things like that. We didn't have Emacs having 30 or 40 years of history or things like that. So now we have these tools that have matured. We have ways of programming that have matured. We have educational curriculum that's sort of ossified. And it takes a conscious effort, and it takes some, in some sense, like a feeling of arrogance that you feel like maybe you could do a better job than all these people who've been working on computing for decades, okay? So I think there's this kind of weird mix of arrogance and humility that it takes to create anything new. You have to have the arrogance and confidence to feel like you can do something of value, and the humility to realize that you don't really know what you're doing, but also the insight that no one else really knows what they're doing either. So that's something I hope you'll think about. All right, so let's talk a little bit about variables. And I am going to use a programming language called Scheme, which is a variant of Lisp. I'm just curious, how many people here know some flavor of Lisp? Okay, a few hands. All right, well, there's not much to Lisp, what I'm going to show you. Well, actually, there's more than, there's a little bit to Lisp, okay? But I'll try to keep it gentle. And I will warn you right now that there are plenty of things that you probably will not understand that I'm going to show you. I understand that's the case. The point isn't to wow you with my knowledge of programming languages or something like that. The point is to try to give you high-level ideas of some things that maybe you haven't seen before and maybe you'll find interesting, or at least you'll get an awareness of these things exist that you hadn't seen before, or maybe you have seen some of these. If you have seen these, I'd like you to think a little bit about what the implications of the different types of variables are and different types of programming paradigms, and start thinking about, are there other things out there to still discover? Okay, so the syntax for Scheme may look a little odd. So we've got the ability to add two numbers, for example. Lisp is infamous for having parentheses all over the place. It's actually not that difficult. We just have parentheses on the outside, okay, of a function call instead of on the inside. So this is just going to add 3 and 4. It's a prefix notation, and we get back 7. Great. Now, if I were programming in what I consider the dominant paradigm, dominant approach, I might define a variable. So like I'll define a variable called x, and I'll say x is equal to 5, let's say. Okay? And if I just type in x, I can reference x, and I find that x has the value 5. Now, if I'm programming in a language like Java, let's say, or a language like BASIC, I might do something like this. I might set x to be 6. And now x is 6. Who here has done this operation in language of your choice? You've taken a variable and then you change this value, right? Okay, that's like the original sin of programming. Okay, this is like the worst thing ever. Well, at least if you listen to functional programmers, right? They're like, that's the worst thing. Immutability is the way to go. All right. So if you're familiar with functional programming, if you're familiar with immutable data structures and the idea that variables should not be modified, you'll know that there's another way to do it. Okay. So this is mutable variables. Okay. So we just change the variable's state anytime we want. And why might that be considered problematic? Any reason we might not want to do that? Threading. Okay, what's the problem with the threading? Okay, so we've just introduced the notion of time into our program, right? So at one point in time, x is 5. Another point in time, x is 6. If you do much math, that's not normally what mathematicians talk about when they talk about a variable, right? It's just like, oh, well, now it's changed. It's not clear exactly what happened or when or why, but x used to be 5 and now it's 6. And if you have one sequential computation running one thread on one processor, maybe it's not so bad. But when you start getting parallelism and concurrency and things like that, it starts becoming a little confusing. It starts becoming difficult to reason about your program, for one thing. Now, that's not to say that you should never use mutable state. This talk is not prescriptive. I'm not telling you what to do. I'm just saying that there are people who find this problematic, or at least think you should be careful when you use it. But I would say that this is the dominant way that people program today. If you pick up most programming books for languages like Java, you will see uses of things like that. And you maybe see a disclaimer, like, you want to be a little careful about it. But that's what you're going to see. Okay, so in this model, I can sort of define this model by when we are going to allow assignment to a variable. Okay? In this model, you can assign to a variable one or more times. Okay, so notice we have the original assignment. We defined x to be 5, and then we did an update So in this case, we basically did 2 assignments. And we can have more assignments if we want, right? I mean, we can have as many as we want. As long as we have at least one. Okay, so here we have 3 assignments. So basically, 1 or more assignments is what I'd consider the dominant paradigm as far as variables go. And if you look at it from the lens of how many assignments are you allowed to make, how many times you're allowed to assign to a variable. All right, 1 or more. Now, if you're familiar with functional programming, then you know that immutability, or not changing the values of variables or data structures on the fly, is considered important. So if you've ever programmed in a language like Haskell, or if you don't have to program in a functional language, you could program in Java or some other sort of imperative language or object-oriented language in a functional way, but in a functional style, we might say something like, let x be 5, okay? So let x have a certain value, and within the body of this let expression, x is going to be 5, so I could do something like plus xx. And I can also say, within the body, let x be x squared. And then give it a new body. Okay, so what's going on here? I have 2 x's. I've shadowed x with my inner let. Okay, so those x's are actually different. I didn't clobber x like I did before. Okay, it's not that x is changing its value over time. It's that I actually have 2 different variables. They just happen to be called x. That's fine. If I want to, I can do something called alpha renaming, is the technical term. And I have to be careful how I change these variables. There are rules for it. But I could change those x to y's, and it's the same thing. Okay? But the idea here is that I'm only going to assign to a variable once, and then I'm done with it. Okay? If I want something new to happen, I have to create a new variable. And typically, these functional languages are based on things like recursion. And every single time I do a function call, a recursive function call, I have a new copy of the variable with the same name. The argument to the recursive call gets a new value. So it's sort of like doing these nested lets. Okay? So in this model, we can assign to a variable exactly once. All right? So before, we were assigning to a variable 1 or more times. Now we're assigning exactly once. All right? Well, so that's kind of interesting. So we have 1 or more, and we have exactly once. Well, what other numbers are there? Could we assign 0 or more times? Or 0 or 1 times? Or infinitely many times? Like, what are these other numbers? I mean, why would 1 be special, or more than 1? Okay, so maybe we can think about trying to do a slightly different model of computation, and we might want to assign fewer than 1 time. Let's see if that works. So I'm going to try loading this. All right, so let's see if I'm going to load a little program here. Great. Hey, it works. All right. So I've just changed scheme, just extended it with a domain-specific language called Minicanron, which is something I work on with many other people. And this is a language for pure constraint logic programming, which we also call relational programming. And if you're familiar with SQL, it's sort of like SQL, where you can have tables that are infinite. Okay, so we have a query language. You can ask questions about tables, but the tables can be infinite, which is different than normal SQL. If you're familiar with Prolog, this would correspond to a pure subset of Prolog extended with certain constraints, with a number of modifications to make the paradigm work better when you have potentially infinite answers. Okay, so I'm not going to spend a lot of time on this language, 'cause I don't have time to teach you all these languages, but I can tell you that we have a little query syntax. So Q is our query variable. We want one answer back. And we have this weird looking operator called equal equal, which performs something called unification. And basically, in this case, we're saying we want Q, the query variable, to be syntactically equal to 5. Okay, is there a value of Q such that Q is equal to 5? And the answer is yes. If Q is equal to 5, then it's syntactically equal to 5. All right, well, it's not very exciting, but that's a thing you can write. I can write other things. I can write stuff like this. All right, is there a value of Q such that Q is equal to Q? Is there such a value of Q? What's the value of Q such that Q is equal to Q? Q, well, any damn thing you please. All right, which we represent as this underscore 0. Underscore dot 0 means anything. It could be anything. So the interesting thing here is I just did a computation with this variable, but I didn't say what the variable was. I said, all right, I just want to write down certain properties or qualities. Q has to be equal to itself. What could it be? Anything. Okay, so I can now start talking about variables without giving them values. So in this version, I can assign 0 or more times. Actually, depending on how you look at it, this is really sort of like functional programming. It's single assignment because once I unified Q with 5 in the first example, now Q is 5 forever. So what I'd really say is that I could assign 0 or 1 time. Okay. So this is what we get with the pure logic programming or relational programming approach. Now, why is that interesting? Well, it's interesting because we can write an interpreter in this using this style that has unusual properties. And I'll show you a couple of those. So for example, has anyone here used Python or Ruby or Perl or any language that has an eval function in it, where you can evaluate an expression? Yeah, okay. So Scheme has this also. So I can type in a quoted expression. So if you remember our +3, 4, now I'm going to add 3 and 4, but I put a quote in front of it. That turns it into data. Okay, so now it's a little bit of program text, and I could say I want to evaluate that program text using eval, and it runs the +3, 4 as a function. So if I just type the expression by itself with that quote in front of it, I just get back the list +3, 4. So eval basically runs that text as if it were a program. All right. Well, what we're going to do is we're going to use eval, but eval written in this style of relational interpreter, or sorry, of constraint logic programming, and we'll see that it can play some interesting tricks. So here is something we can do. So we can write, instead of eval, we can write eval-o, and I need to have my run Q wrapped around it. Okay, so I can eval something. So I could do something like a lambda expression, if you're familiar with lambda expressions. It creates an anonymous function. This is the identity function, lambda XX. And I could say, what's the value of that? So instead of having an output, we instead place a variable in the second position of eval-o. That's similar to returning a value just from a function or a method. And so we'll see what's associated with the, run 1, I want one answer. We'll see what's associated with Q, the query variable. All right, so that lambda expression evaluates something called a closure. So if you're familiar with functional programming languages, a closure is just a representation of a procedure. Okay, it doesn't really matter. But what's more interesting is that we can decide where we want to place these logic variables. So what I can do is I can say, all right, well, I know that returns a closure, lambda XX. When you evaluate it, it gives you back a closure. Well, I could put the logic variable in another position. I could say, well, if I know the answer is this closure thingy, whatever that is, what must have been the original program, the original expression? and it'll say it's lambda xx. Huh, well, that's kind of interesting, so I just ran it backwards. All right. Now, what are interesting things we can do? Here's an interesting thing we can do. Do you know what a quine is? A quine is a program that evaluates to itself. This is like a standard hacker trick. Okay, you write a program, you run the program, the result of running the program is the program itself. It's kind of fun. All right, so my question is, can we write a query here that will generate a quine, a program that evaluates to itself? How do we do that? Any ideas? Okay, so we got the eval call, and what are we going to change? Make it as a string and pass it to itself. Okay, the idea of passing something to itself is the key here, right? We have to have some sort of referring to itself or something similar to that. It turns out that we can do something much simpler. Okay, what we can say is, well, what we really want is for Q to be a program and the output of evaluating Q to also be Q. How does this work? Magic, I don't know. Well, let's just see what happens. If I run it, okay, we get the stuff that's a little hard to see. Let me just grab the front part of it. Okay, so that's maybe a little easier to see. So we have this kind of weird expression. And, well, first of all, you see that _0 thing again? Okay, so that's a representation of a variable in our language. In Scheme, saying it doesn't matter what we call that thing. So just to make it a little easier to read, I will change that to be called x. Okay, so this is our program. So we have a lambda expression, and it's calling list. List just produces a list, and it's got a quote of quote, which looks kind of weird. And then this other lambda expression has a quote in front of it, so that's treated as data. Oh, I don't know. Let's try running it. Oh, we get back the same thing. Oh, well, that's kind of weird. So we just typed in the definition of what a quine is. It's a program that evaluates to itself. So we typed it in, and we got back, as the output, a quine. We didn't have to know how to write this, right? I'd have trouble writing that if you sat me down. But just by being able to put logic variables in different positions in our expression up here, we can get these sort of unusual behaviors. Okay, so this is the power of being able to work with variables that can be assigned 0 or 1 times. We don't actually have to have a value for the variable before we use it. I'll show you a somewhat more sophisticated example of this. This is a tool called barliman. I've been working on this with Greg Rosenblatt and Michael Ballantyne, various other people for a while. And so the idea here is that we can write some scheme code in the upper left. So we're going to define a function that concatenates 2 lists, that appends 2 lists. And the way we're going to do it is by just writing tests. So if you're familiar with test-driven development, you're supposed to write your tests first. Well, we'll do that. So in Scheme, the way you append a list is by calling a function called append. Okay? And you give it a list. So the smallest list we can append is the empty list to the empty list, and that's supposed to return the empty list. So I can just write the input and the output, and the system comes up with, all right, the best guess is you're defining a function called append. Lambda _0 is saying, okay, I don't know what the arguments are. It's probably variadic. It take any number of arguments and returns the empty list. Well, that works, but that's not as sophisticated as we'd like. So let's give it another example. So we can say append, how about cat to squirrel. Oh yeah, so those are supposed to be in lists. List cat to list squirrel, and cat squirrel. Okay, so, did I spell it right? Oh, I need a quote. Good. All right, and it came up with a program here. And now you can see it's got a list of 2 arguments, _0 and _1. So I say, okay, append as a function takes 2 arguments. If the second argument is the empty list, return it. Otherwise, return the list cat squirrel. So it's overly specialized. All right, it's overly specialized. We could try to fix that in various ways. So we could say, dog, mouse as another example. We can give it multiple examples. Dog, mouse. And so if we give it a second example, that'll keep it from over-specializing. Now you notice the program it comes up with doesn't specialize. But there's another way to avoid over-specialization, and that is to introduce or define or use another notion of variable. Let's use a different notion of variable. We're going to use what's called an eigenvariable, also known as a Skolem constant. In this case, we're kind of faking it using something called a gensim. So what we're going to do is we're going to have a fake value. I'm calling it G1 and G2. These effectively are eigenvariables. So what these represent are universally quantified values. And so basically what this is saying is, I don't know what G1 is. I don't know what G2 is. It doesn't matter what they are. You're not allowed to look at them. Okay? You can put them in a list, but you're not allowed to compare them with other things. You can compare them with themselves. You can compare them with a logic variable that doesn't have a value yet, but otherwise nothing works. Okay? And they also have lexical scoping. So you can see the same behavior. Now I don't have any G1s or G2s. I use this weird eigenvariable thing. Oh, all right. It's because I want to have something universally quantified. I want to say that this is true for all G1 and all G2. I don't want to tell you what G1 and G2 are. I'm not going to tell you whether they're cats and squirrels. I'm saying it doesn't matter what they are. Just treat things based on the structure. All right. And let me do one more example now, because we have the structure of the program, but we don't have a recursion yet. So let me do one more. So let me do G3 and G4, and G5 and G6. G6. All right. Let's think about that for a minute. 3, 4, 5, 6. Garbage in, garbage out. Make sure it's right. Okay, there we go. And so now it has a recursive call. And so this is a correct definition of append. And just to make it a little easier to read, I'll give some concrete variable names instead of abstract variable names and let it think about it again. And now you can see a concrete definition, and that is the definition of append. Okay, so we're doing example-based program synthesis, but underneath the hood, this is exactly the program I showed you before, that eval thing. That's all it is. So this is all based on the idea that we can put variables in different places and the system will fill in the values. We don't have to give the values right away. And that comma A here and that comma C, those are logic variables. Those represent holes in our programs that are unknown. So we're reasoning about code that has big chunks that haven't been filled in yet. We can run tests on code that hasn't been filled in. We can have the computer fill in missing things. And notice that we have several notions of variable here. We have those eigen things that represent universally quantified variables saying, hey, for all G1, all G2, this is true. And then we have these logic variables. And the logic variables can be assigned 0 or 1 times. The eigen variables, those G1, G2 things, in some sense can be assigned exactly 0 times. They can never be assigned a value. They represent metaphorically an unknown value, an always unknown value. Or you could argue that maybe they can be assigned exactly once, you can think of it that way, but you can never know the value. But in any case, so now we have the notion of an eigenvariable or a Skolem constant, and that can be assigned arguably 0 times. Okay, so we have a notion of a variable that can be assigned 0 times. And at that point, if we want to kind of look at things, so we could make the argument that we actually have a stack, talk about full stack development. We have a stack of software that barliman is based on, and each layer of that stack has a different notion of variable based on how many times you can assign to the variable. So at the very lowest level, you have Shea scheme, which is implemented in both Scheme and the garbage collector is written in C. Okay, and if you look at the code for Shea scheme, which is available on GitHub, you will see that it uses mutation, it uses setbang, and the C code certainly has side effects in it, and mutation. So the variables in Shea scheme are based on sort of the standard paradigm we have, where you can assign to a variable one or more times. Minicanron itself, the logic programming language that we build evalu on, that is written in a purely functional style. There are no mutations, no side effects. So every variable in Minicanron's implementation can be assigned exactly once. The relational interpreter, the evalu thing, is written in a logic programming system, and those variables are logic variables that can be assigned 0 or 1 times. And then with the synthesis query, when we're trying to synthesize a pen, we use those Eigen variables or Skolem constants, which can be assigned exactly 0 times, is one way to look at it. And also it uses logic variables in the query, which can be assigned exactly 0 or 1 time. Okay, so you see different notions of variable based on how many times you can assign to it. Now, let me show you yet another way to talk about variables. We can do something similar to what I just showed you in terms of having something like a evalu, but in this case, we're going to use what's called abstract interpretation. Who here is familiar with abstract interpretation? Anyone? Abstract interpretation? Okay, so I saw one hand. Abstract interpretation is sort of like interpretation. If you write an interpreter that can take a program and run it. But the idea with abstract interpretation is that when you're writing an interpreter or you write a program that's going to be interpreted or compiled and run, you've got a problem when you want to do things like testing. So what's the problem with testing? Why isn't testing so great? It can find bugs, but what can't it do? Well, it can't fix them, but what else can it do? Well, logic error, maybe you can find them, maybe you can't, but it can't prove that your program doesn't have bugs, right? It can only say that for a certain input you have bugs. But if you're writing a program, anything other than the most trivial program, the set of possible inputs is so vast that there's no way you can test all the inputs, right? So that's why you can write some test cases or use JUnit or whatever, and guess what? Your program still could have errors in it, right? And so the problem is you effectively have an infinite number of inputs, but you're only testing a finite number of inputs with your tests. So abstract interpretation is based on the idea that, well, we can't solve the halting problem. We can't prove properties for universal computing for all possible inputs, but we can be conservative. There are certain programs that we can prove certain properties about for all inputs. As long as we're willing to be conservative, we can't prove everything we'd like to, but we can prove something. So we can abstract the notion of the input. So for example, if we want to reason about what happens when we have integer arithmetic, a concrete program would actually deal with addition or subtraction, multiplication, so forth, over concrete numbers, like 3 plus 4. An abstract interpreter might abstract over the notion of those numbers and say that instead of having numbers like 3 and 4, we are going to divide all integers up into 3 classes. A class of positive integers, 0, and negative integers. And we're going to have an abstract notion of addition. We're going to have an abstract notion of multiplication and subtraction and so forth. So if I add a positive integer to a positive integer, what should I get? Positive integer if we're not worrying about overflow and signed integers and C and stuff like that, right? So we'll pretend that we're working with big nums and arbitrary precision arithmetic. So if you add two positives, you get a positive. What if you add a positive and a negative? What do you get back? You might get a 0. What else might you get? Yeah, so you get a set of values back. You add a positive and you add a negative, and you get back a set of negative, 0, positive. So now you're actually dealing with sets of values. So each variable, each abstract variable now, gets an abstract value, which is actually a set of values. And when you try to do something like abstract addition, now you get back a set of answers. Okay? But the advantage of this approach is even though you lose precision, that's the technical term, we now can't talk about 3 and 4. We can only talk about positive numbers or negative numbers or 0. The advantage is by sort of squinting and saying, okay, 3 is a positive number, 4 is a positive number, but now we can actually prove certain properties for infinitely many inputs. That's the advantage. Okay, so we lose some precision, and it also can be quite slow in many cases, but we can get some advantages of proving things for all possible inputs, which we normally can't do with testing. So I will show you a quick example of this. Okay. I have loaded my relational abstract interpreter. This is, by the way, written in Minicanron. So it runs backwards, although I don't think I'm going to have time to really show that. So this is a concrete implementation of the Fibonacci function, which is one of sort of the two hello world examples in functional programming, the other one being factorial. Fibonacci is a little more interesting. So the idea is that we have a number coming in. If the number is 0, we just return 0 or n. If the number is 1, which I've written as if n minus 1 is 0, then we return 1. Otherwise, we make 2 recursive calls and add the results. So we recur on n minus 1 and we recur on n minus 2. We add those results. Okay, so that's cfib. And I can show you a call to cfib. This is concrete fib. So cfib of 6 gives you back 8. Okay, and that's the same as if I added cfib of 5 to cfib of 4, that's also 8. So that's how factorial works, or Fibonacci works. And it doesn't really matter, but the point is, it's just a simple function that does mathematics. We also have an abstract version of fib. So here's written in sort of a tagged way. You can see these lambs and int tags. That's just because of the way we wrote the abstract interpreter. That's not really important. It's the same program with one change. And that change is that we now have abstracted over the numbers. So if you look at the concrete version of fib, in the second recursive call, I'm subtracting 2 from the value of n. And if you look at my abstract fib, I'm just subtracting 1 in both cases. That's because I now only have basically 3 classes of numbers. Positive, which I'm always going to represent as 1, 0, which I'm going to represent as 0, and negative 1, which represents any negative number. So here's int 0, int 1, and int negative 1. Those are my only numbers I'm allowed to have now. And I'm going to go ahead and analyze a call to Fibonacci of 1. Remember, 1 represents any positive number. So this is equivalent to calling Fibonacci on any positive number you could possibly imagine, a 100-digit long positive number. It's the same thing as calling on 1. Right? So let me try calling this thing. It's kind of slow. All right. So we get back this thing, which is kind of hard to read. It gives you a bunch of information. It's a little too much. So what I'll do is I will write a query which kind of throws away some of the side information that we don't care about, because right now, all we really want to see is whether or not we have positives, zeros, or negatives. And then this particular abstract interpreter is giving us 3 values back, and it's saying that, okay, one abstract execution of the program can give us positive, the set containing positive numbers, one can give us a set containing 0, and one can give us a set containing positive numbers, and you have to take a union of those. So basically, this is saying that a call to Fibonacci with a positive integer will give us back either a 0 or a positive integer. There's no way to get a negative integer back. Okay? There's no way to get a negative integer back. And this is a proof over infinitely many positive integers. So we've ruled out a class of behavior. We know for sure we'll never get a negative behavior or a negative value back. And this could be useful, for example, if you're writing an optimizing compiler and you want to leave out a negative bounds check, that kind of thing, if you have an array index and so forth. So, or for security purposes, abstract interpretation is often useful. So now we have another notion of variable. So in this case, we have these abstract variables that are associated with abstract values, and the values themselves represent infinitely many possibilities. Or, in the case of 0, it represents exactly one value. Okay? So now, when we assign an abstract value to an abstract variable, we can assign effectively 1 or infinitely many values, or infinitely many times, depending on how you look at it. Okay, so we've introduced the notion of infinity now in our assignments. All right, and I've got one more to show you. So let's look. Yeah. All right. One more. I could do this all day. There are lots of notions of variable. Lots and lots of notions of variable. Okay, so what I just loaded is what's called a reducer for combinatory logic. Anyone here use combinatory logic or familiar with combinatory logic, like combinators or SKI, calculus? A couple hands. Okay. Doesn't really matter. It's just, this is another system of computing. Who here has heard of a Turing machine? Okay, a lot of people have heard of a Turing machine. How about lambda calculus? Okay, so those two turn out to be equivalent in computational power. Okay, they're both so-called Turing complete. Combinatory logic is Turing complete. Okay, so it's another model of computation. It's not as commonly used as, say, languages based on Turing machines or lambda calculus, but it's actually very closely linked to lambda calculus. Okay, so let me show you what one of these programs look like in combinatory logic. Here, this beautiful thing right here, that is actually a program in combinatory logic. Okay? So if you work in combinatory logic, that's what all your programs look like. This is using what's called the SKI basis. Actually, you don't need the I. You can just use S and K. And turns out there's another basis called the X combinator. And so if you write your programs using the X combinator, basically all your programs look like things like that. Okay? Imagine pages and pages and pages of X's and parentheses. And it turns out you only need one parenthesis. You don't need both. And then you can use combinators called push and apply. And so your programs look like that, okay, which is sort of like binary. Okay, so this is a lovely way to program. And so I'm going to reduce that program. Okay, so that program I showed you, this S applied to S, and so forth. And these are all the possible reductions of that program. So these themselves are all programs. They all turned out to be equivalent in some sense, okay? So this is your life if you're programming in combinatory logic. You notice what you don't see in combinatory logic? You don't see assignment. Why don't you see assignment? There are no variables. There aren't variables at all. There are no variables. You don't need variables to do programming. You absolutely don't need variables. Certainly the machine doesn't need variables to do programming. Variables are unnecessary. Names are unnecessary. Okay, you don't need it. So in this model, you just don't have variables at all. Problem solved. Okay, and I'll show you. Remember our friend Eigen that I was telling you about before? The last time we were faking the Eigen. This time we're going to use a real Eigen. So this version of miniCanron has Eigen built in. Okay, so what this is equivalent to is a type of query where we're trying to do program synthesis, and we're trying to answer this question. So let's see if we can get this. All right. So we are trying to find something called a fixed point combinator. And there's this magical equation right here that we're trying to solve. Has anyone heard of the Y combinator? The paradoxical combinator? Okay. It's also the name of a company or something, but the real Y combinator is what's called a fixed point combinator, and it allows you to do effectively recursion. And this is the mathematical or logical definition of the fixed point combinator given by Byrd in his book on the lambda calculus. And it reads like this. There exists some function f, or some combinator f, such that for all x, f applied to x is equal to x applied to f applied to x. Okay? So this is a theorem, but it doesn't tell you how to find such an f, such a combinator f or function f. So we're going to find one. We're going to find one through the power of logic programming using this query. So here I'm giving it a little bit of a hint. Just in the interests of time, I'm saying, okay, that function f, the combinator f, it itself is composed of a smaller combinator u applied to itself. Okay, I could take that out, but it would take longer. It would take like 15 minutes. I know some ways to speed this up, but I haven't implemented yet. But anyway, the point is, if you look at this query, we're trying to find a combinator f that has this property that f of x is equal to x applied to f of x. That's their mathematical definition. And you notice that there are two types of variables. One is a fresh variable. This introduces a new logic variable. Remember, logic variables can be assigned 0 or 1 times. And it introduces a new eigenvariable, x, representing all possible combinators, or all possible terms. And that represents infinitely many terms. So that can be assigned 0 times. And now we're going to run this thing, and we'll see if it comes up with a combinator for us. Hopefully. You can do it. You can do it. I think it takes about 30 seconds. So if this comes back, which hopefully it will, there we go. Here's another beautiful program. So that combinator is equivalent to the Y combinator in lambda calculus. This is a fixed point combinator. This allows you to do recursion. And notice it's all composed of S's and K's and I's and procedure application or function application or combinator application. Okay? No variables. Have no variables at all, no notion of assignment. It's Turing complete. You can do any sort of mathematical or logical computation that you can do in Java or whatever using this approach. And in our query language, we had fresh logic variable can be assigned 0, 1 times. An eigenvariable can be assigned 0 times. And then we're outputting combinator terms that don't even have a notion of a variable. Right? So if I go back to my list here of possible notions of variable. Okay, so originally we were synthesizing append, and we had these various notions of variable. We did some abstract interpretation. So then we had the notion of abstract values, which could represent infinitely many concrete values. So an abstract definition of Fibonacci ended up using these abstract values that could represent either one value, like 0, or infinitely many values, such as all positive or all negative values. And we were able then to rule out infinitely many values, that there's no way to get a negative value out of that definition of Fibonacci. And we still had it built on the stack of other languages and technologies that had different notions of variable. And then finally, the last version I showed you with combinatory logic, that also has a stack. So the bottom part is similar. But now, the fixed point combinator that we synthesize has no notion of variable at all, has no notion of variable assignment, obviously. And we were using Eigen as the fixed point combinator, so that query used both regular logic variables that can be assigned 0 1 times, and Eigen variables that can be assigned exactly 0 times. And I could spend all day telling you about different notions of variable. There are hundreds of notions of variable that I know about. This is just one way to look at a few notions of variable. And I'm sure that there are many thousands of notions of variable that I don't know about, because each year I learn about new notions. And each notion of variable is trying to solve a problem that people have. Okay? And there are many, many, many notions of variable yet to be discovered, I'm sure. And my point isn't to say that you should use combinatory logic for everything. Okay? My point is to show you that there are many ways of approaching computation that go outside of what we think of as sort of standard programming approaches and standard programming languages. And if you look at programming from the viewpoint of something like these variables, you will see that if you know Java and you know C++ and you know C and you know Python, in some sense you know one approach to programming. And there are many, many others. And that I hope as a field, both for fun and intellectual enjoyment, but also so that in the future we can have different types of abstraction and different capabilities than we currently have, that people are going to, sort of break out of the current default mold, which I consider to be, to some extent, similar to how we ended up with Unix and Windows. I mean, it's not to say that there's nothing fundamental about a Turing machine. There is, but there are many other models of computation that have properties that are nicer than that of a Turing machine for certain things. And a language like C is actually quite close to like a Turing machine in terms of the way you reason about your programs. So I'm hoping that you've seen at least one thing you haven't seen before and that you'll want to play with. And I'm hoping also that you will be inspired to try to think a little bit about whether you know what a variable is, whether you know what a programming paradigm is. The next time you think, here is the way to do it, well, is that really the only way to do it? And you'll spend at least part of your time thinking about other approaches. Okay? And maybe you will go off and discover the next notion of variable that we can use to do other types of interesting computation. And you'll discover some new programming paradigm, and you'll do things like program synthesis or artificial intelligence, hopefully not the robot uprising, but you'll come up with things that are going to open our eyes as to what is possible with computation, because I think we're really only beginning, and we shouldn't think that we actually know how to program. All right. Thank you.